Okay, I want to give a complete overview, or a basic overview, of the relation between the return waves and exhaust in an expansion chamber and the timings of the engine. By timings, I mean the timings of the ports when they're opening and closing. As this is a graph from my expansion chamber calculator. It shows the trailing exhaust pulse after the transfers open, and the diffuser wave that starts a little bit before bottom dead center and ends around transfer closing, and the baffle wave that starts then and ends later on after exhaust closing. If you look at this drawing down here, the bottom exhaust port basically is BDC. Usually the pistons, even with that at BDC, bottom dead center. The transfer, which I've drawn here on the right side instead of it over here like it should be, it shows the top of it is transfer closing. As the piston rises and it closes off the port, that's TC. As it rises some more and closes off the exhaust port, that's exhaust closing, EC. So in an ideal world, this right here is a representation of what would happen between bottom dead center and transfer closing. You would have additional suction applied through the exhaust port to the cylinder. And after the transfers are closed off and the piston is rising, you would have additional pressure until exhaust closing. This being because as the piston rises, it squeezes some of the intake mixture out the exhaust port. But if you have a rising pressure here equal to the rising pressure here, you're not going to have that loss. So you have more fuel air mixture to burn. And what happens with the negative pressure, as this piston is rising from BDC to TC, it naturally causes a suction in the crankcase, which will pull the intake charge, which previously was squirted up through the transfers into the combustion chamber, pull some of it back down, which is not what you want. With the negative pressure applied here at that time, it'll keep intake charge coming in through the reed valve into the crankcase and keep the mixture flowing up into the cylinder. Some of it additionally will be lost at the exhaust port, but the beginning part of that mixture anyway is a mixture of fresh intake charge and spent exhaust gases that have little to no oxygen. So it's a very oxygen poor mixture here. So to hell with that. So I don't know if this little graphic's going to be helpful right here, but when you look at this graph on my calculator, just imagine the piston as it's traveling, closing off the transfer port, and then eventually closing off the exhaust port, going up to TDC, and then coming back down. But the graph starts at transfer opening, which would be right there. Okay, transfer opening. Down to BDC, and then it comes back up. So that's that. Now, let me show you. This drawing shows an expansion chamber with a two-stroke engine fed by a reed valve, and this drawing also has the transfer to the rear, just for understanding the function of it and how it relates to the pressures. So when the intake charge is squirted up from the transfers, it's up here. Some of it gets lost as the piston rises. Now the exhaust is closed. It's starting to compress this so that it can be combustible. The spark happens and that starts to quickly ignite. The pressure increases as that fuel burns, and it pushes down on the piston. The exhaust gas goes out the exhaust port into the pipe. And as that exhaust gas passes the diffuser cone, it causes an inverse directional suction wave, which is represented by the green minus signs. So you got the suction wave that comes back right as at top RPM. Everything changes with different RPM, but we're saying that this pipe is tuned right for top RPM at peak RPM. When the piston's at bottom dead center right here, the beginning of this suction wave will just begin to reach the cylinder. And the lowering piston causes a positive pressure here, which pushes the intake charge up through the transfers into the cylinder. The exhaust gas passes the baffle wave and causes an inverse direction of a positive pressure wave following the negative pressure wave. Okay, the negative pressure wave has entered the cylinder, the transfers, the crank, which is all good. It causes more intake charge to come from the carburetor through the reed. And it's drawing out the beginning of that charge that was mixed with the exhaust gas, which is poor, low in oxygen. Okay. Next, we have the piston rising, closing off the transfers. As it rises, and this whole system becomes sealed off from this system, it causes a vacuum, which pulls in more intake charge into the crankcase. As it's beginning to pressure this, you get a slight positive pressure here, and the positive pressure wave from the baffle just now is beginning to come. And what it will do is it will push a little bit of this intake charge back in, and the positive pressure here will not completely but somewhat match the increase in pressure that this wants to happen as the piston rises. So as this pressure matches this pressure, you have less loss of intake charge out the exhaust port. So it's a supercharging effect. It's increasing the dynamic compression of the engine. So it's a twofold effect. It's causing the retention of intake charge here and an increase in compression ratio. And then we're back to where we started. Pressuring the intake charge again. This right here is sheet 3 of my expansion chamber calculator. Once again, you see the diffuser wave and the baffle wave. BDC, transfer closing, exhaust closing. This peak RPM is 9,500. Okay. Down to 8,500. the wave is still very effective in the time between transfer closing and exhaust closing as the piston's rising. But it's beginning to cause a detrimental effect here when the piston's rising. Let's say exhaust closing at 180, so it's basically about halfway between bottom dead center and top dead center, which would be around here. So as that piston is rising, it's starting to cause a suction underneath it. And you want the diffuser wave, the suction wave from the diffuser to augment that, to be in harmony with that. And if you get a pressure wave or a section of the pressure wave happening before transfer closing, that is going to cause some of the intake charge that's been sucked up into the cylinder because of the suction wave to be pushed back down the transfers. So as this becomes more predominant here, it lowers power, because the power is an equilibrium between intake charge and compression of that intake charge, both in intake and supercharging. So I'm going to put lower RPM here, 7,700 RPM. At this point, you've lost the pressure that you need when that exhaust port is being closed. So as the piston's rising, some of that intake charge is squirting out the exhaust because you don't have the positive pressure here to resist it. So this is the end, or this is actually the beginning of the pipe power band. So in this example, the pipe power band is from 7,700 to 9,500, which is 1,800 RPM. And you see it's predominating more as opposing the flow of intake charge up through the transfers. This positive portion of the wave is going to be pushing that intake charge back down the transfers. So it's going to be lowering the delivery ratio, the amount of intake charge that's going to be later compressed by the piston. So if you've ever noticed the power dip that happens right before the pipe power band, usually for about 1,000 RPM, that is because this is happening. So let's say from 7,700 for 1,000 RPM to 6,700, boom, look at that. All of that wave is right there. Not much is happening for this first section right here as the piston's going through this number of degrees. This is 180, this is 90, this is 45. First 35, 40 degrees, the piston's not hardly rising at all. But then from here on out, it's steeply increasing in speed. So this wave right here is the cause of the pipe, the pre-pipe power band power dip, which can only be offset by a boost bottle. And there are pipes without a baffle wave to just have the benefit of the intake charge, and you never have this happen. You never have a dip in power. My Suzuki AX100 was close to that design, not quite. It had a very long belly section before the baffle, which caused this wave to be located over here. So only at about 4,500 RPM, it would be over here, which at that low RPM, it's negligible, its effect, because you have so much more time from transfer closing on up for the process to happen. On high RPMs, it's more critical because you have so much less time to deal with. You're talking about milliseconds. So I hope this pretty much explains what is happening with the pipe in relation to the ports opening. These waves, I want to explain something else about the belly. These waves seem to be happening one right after the other, even though there's a belly of 230 millimeters, which is approximately 9 inches. So why are those touching if you have so much space between them with a belly of 9 inches? It's because the exhaust wave is not just one thin wave that's happening. It's a long wave. It's like anywhere from 0.6 milliseconds up to maybe a max of 2 milliseconds. So it has an effect of creating a longer, in conjunction with the angled cones, it creates a reverse wave that's longer than it is. So it spreads out. So that spreading causes what would normally be here over here, and with the baffle wave would normally be here over here. And so they touch. If the belly is too short, and just ignore this 230. Every pipe and every engine is different. The spacing between TC and EC is different. The RPM is different. You have to know. You have to have a program like this to know exactly what's happening and how to set that belly. Some people use the trial and error method of just saying, well, this worked okay on my 125, so we'll just make it this way for this 125. And it's not highly critical. You have a big margin of error when you're designing a pipe. But if you're racing and you want the absolute best power, or the power band suited just right for the track, or whatever other detail you're hunting for, you have to know exactly what's going on, exactly what the best way to do this is. If that belly is too short, these two waves will actually run over each other. You put those two close, these cancel each other out. So the actual wave is like, what happens is it becomes like this, and you've lost that potential use of that energy. You've lost energy, basically, even though it makes for nice power at the very top RPM. Like if you get a drag bike and that's all you do, you just use the clutch and you just throttle the hell out of it, and it's at the top RPM, and that's all you use to the end of the quarter mile. This would be good. You want a short belly for that. If you get an enduro bike, you don't want to waste anything, because you want both of these waves to be as long as possible for as long a possible power band. So you want a very long belly, and then all different types of bikes in between. It depends upon what you want. So you have to look at the you have to look at the pipe power band, which is what this shows right here, the pipe power band. This one being from 6250 to 8750. And so I guess that's all I want to teach on this session. Thanks for watching.